Welcome back to Geology Dean's Optical Mineralogy series. In our final episode, we're taking everything we've learned and putting it all together. We've mastered identifying minerals under the microscope, but optical mineralogy is so much more than just putting a name to a crystal. It's about becoming a geological detective, a storyteller of Earth's deep past. Think about it. Every thin section you hold is a snapshot, a moment frozen in time. The minerals present, what we call the mineral assemblage, are like a list of characters in our story. Some minerals, like kyanite, andalusite, and sillimanite, are fantastic clues. They tell us about the pressure and temperature conditions the rock experienced. Finding one of these tells you a specific chapter of the rock's journey, whether it was buried deep within a mountain range or heated near a magma chamber. But the plot thickens when we look at the textures. How are the minerals arranged? Are the grains randomly oriented, or do they show a preferred alignment, a foliation? This alignment screams deformation. It tells us the rock was squeezed and sheared under immense tectonic forces. Imagine continents colliding, and you're seeing the evidence right there, at a microscopic scale. Are the grain boundaries sharp and straight, or are they irregular and sutured? This can indicate whether the rock cooled quickly or slowly, or if it underwent recrystallization deep within the crust. We can even see the sequence of events. Sometimes you'll find one mineral enclosing another, what we call a poikiloblastic texture. This tells you which mineral grew first. You might see large, early formed crystals, called phenocrysts, that have been broken and fragmented by later deformation. This is like reading a geological timeline. First, the magma cooled and these large crystals grew. Then, tectonic forces kicked in and shattered them. Later, new, smaller minerals grew around these broken fragments. Each texture is a sentence building a narrative of heating, cooling, pressure changes, and deformation. By combining all these observations, the mineral assemblage, the textures, the deformation features, we can reconstruct an entire geological history. We can say, this rock started as a sedimentary shale, was buried during continental collision, heated up to 600 degrees Celsius at a depth of 20 kilometers, was then deformed and sheared as the mountains rose, and finally was brought back to the surface through erosion, all of that from a single 30-micron thick slice of rock. It's an incredibly powerful tool. You're not just looking at pretty colors. You're deciphering the epic story of our planet's evolution. Thank you so much for joining me on this journey through the world of optical mineralogy. I hope you now see thin sections not just as samples, but as geological stories waiting to be told.